we have now assigned a TA to each of your projects. So you should be hearing from your TA within like the next 1 or 2 days. If you don't hear from your TA, please check. At least for now, you should just expect, hey, I'm your TA. If you have any questions, please contact me directly. And so by the end of the week, beginning of next week, we want to give you either written feedback or you can also make an appointment with your TA to get individual feedback on your project. So you should kind of understand your project at this point as a kind of an ongoing negotiation between you and your project supervisor. We also don't hold, like I do, but the DAs don't hold any standing office hours anymore. So you can still come to my regular office hours with any concerns that you might have Thursday after class, but there are no technical office hours by the TAs anymore. So if you have a question about anything that is related to D3 or to your project implementation, please simply make an appointment with your TA that you will get to know soon. And if you don't hear from your TA, check your spam, or if you still don't hear from them by the end of the week, shoot me an email when something went wrong with the communication. Any questions about this process? Okay, great. So if you, this is a table from Tamara Mansell's book of these major data types, and today we'll be talking about how we can visualize tables. We have seen a lot of table visualization without formally talking about them, so some of the things like parallel coordinates or bar charts or scale plots, you're already familiar with them, but now we think about it in a little bit more formal way. So what you can do with tables is, first you can simply express values. So that's the simplest case, where you have just a value and want to express the value and don't consider keys in your table. If you do consider keys, there's 3 different steps. Now, this is if you read the book chapter, this is kind of like a good way of thinking about it, but it might not be the most natural way to think about it, is separate, order, and align. Then here, we look at how many keys do we have, right? We talked about tables can be basically just tables with records and dimensions or attributes. But a table can also be multidimensional, like when we have a homogeneous data set with 2 sets of keys, so that we could represent it in a matrix. Or with multiple sets of keys, we could in theory represent this as a volume, and if we have many keys, you could do some recursive subdivision, for example. So we'll talk about this. One of the examples for recursive subdivisions is scatter plot matrix. Then a key way of arranging tables is choosing your axis orientation. So there's rectilinear orientation, there's parallel orientation, and radial orientation. And then we'll talk about layout density, where we have either dense or space-filling layouts. This is just a reminder that spatial channels are the most effective for all attribute types. And when we talk about tables, we kind of have to choose, since there's no natural spatial distribution here, we have to choose our variables manually, and of course we're going to use space in some way or another. And so we will think a lot about, for magnitude channels today, how do we visualize this? Position on common scale, position on unaligned scale, length, and then for the keys or for categorical attributes, we'll use spatial region. And then also recall from the data lecture about attribute semantics. So when we arrange tabular data, attributes are chosen to be keys and values. So typically, the most common forms of table is that we have key, items in rows. We have a key here that can also just be the index of the row, and then we have the attributes, these dependent observations about these independent variables in the columns of the table. And so here in the center we have a cells containing the value, and that is of course equally valid in a multidimensional table. One thing that if you try to visualize tabular data, your choice is going to significantly depend on the scale of your data set. So if you have a table with 50 dimensions, it is very different from if you have a table with more than 1,000 dimensions. The same is true for records. If you have about 1,000 records, just using visualization without any computational means is fine, but if you have, let's say, more than 10,000 records, you typically need something, you need to do something first, like we talked earlier, like last time, clustering, filtering, querying, aggregation, things like that. And so we'll be talking a little bit about this distinction. And then what also drives your choices on how to visualize tabular data a lot is homogeneity of your table. So if you have, let's say, a table with blood pressure at several time points that you've taken over the course of multiple years, this is a very homogeneous table, right? All of the dimensions have the same scale and so on. But if you have a lot of information about these people, like what is their fitness club, how old are they, how big are they, what is their score in school, and so on. So then you have these very different dimensions, and you have to make different choices about your visual encoding. So yeah, this is this example. So I like to classify visualization techniques based on how much of an analytical component you need. So there is techniques like scatterplot matrices and parallel coordinates where you don't, strictly speaking, need any analytics. You can just plot the data as they are. You can still use analytics. So you can use clustering techniques to highlight like the colors here in the parallel coordinates, but they're strictly speaking not necessary. Then you have these like pixel-based visualizations and heat maps, which are essentially useless if you don't use smart ordering. Like we've seen this in matrices many times, that the ordering is important. And then we have visualization techniques that are basically really living by an analytical component. So like multidimensional scaling, if you remember the case study we did on musicians and how they're related, or philosophers, how they're related. Here we have like a model that we fit in some way, or we have like a dimensionality reduction technique, and we show only a highly derived data set instead of showing the raw data. And so we'll talk a bit about those too. Okay, so let's take a step back. If I just wanted to express values and don't consider any keys, the simplest version of that is of course the scatter plot. So here I'm plotting life expectancy versus inferred mortality, and scatter plots are very great to read because we see there's a linear relationship. The higher the life expectancy, the lower the child mortality. You can, of course, use additional attributes in scatter plots. So this one here uses the bubble size to encode the size and the population in the country, and the color to encode the continents. We have seen this in Gapminder before. One interesting thing that you can do with scatter plots is to add regression lines, so that you have, under the assumption that you have a linear relationship between your variables, you can try to fit a regression line. You probably know how to do this. You're trying to find this line y, where you have a beta 0 plus beta 1 multiplied by x. And you can fit a line that essentially minimizes the squared error of distances of each of these points to the line. So you can use the least squares algorithm to do that. Generally, this is a good idea. I kind of like this interpretation. I don't trust linear regression when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations in it. So, the point here is that you can always calculate a linear regression, but you should always also visualize your data. And so this combination of a statistical approach and the visualization approach here can be very helpful. And just to illustrate this point a little bit further, reminder of Anscombe's quartet. Here you have these linear regression lines. And you can see, this is basically the assumption that you would make about this data if you don't know more than this regression line. But you can see that we have these obscure trends, and they still fall on this linear regression line. Okay, so next we'll talk about encoding one key attribute. And so the thing to do here is, of course, bar, dot, and line charts. Okay, so first we separate, this first step here is separating. So we do, we make a spatial choice about treating each of these keys in a distinct area. So that we could, for example, assign a random position that just doesn't overlap, and then we would have the separation. But we can also order them, for example, in a data-driven way, and then we can also align them. And so here we have a line chart, and here we have an aligned and ordered chart. And for the line chart in this case, of course we have a more natural order. This is not a completely categorical, it's actually not a categorical data set, but an ordinal data set, so we don't have to make this choice of ordering And all of these values are on the same scale, so that is kind of an easiest thing to do. So if you want to encode multiple keys and attributes, we can go into matrices, volumes, and then recursive subdivision. So this is an example of recursive subdivision, a stacked bar chart. Here we have, this is a Titanic data set that we already mentioned before. We have like first class, second class, third class passengers. And then like this is one key, the class, and the other key here is survival. So did they die or did they survive? And this also juxtaposes two different approaches to showing this in this bar chart. The one here is absolute numbers, and then here we have proportional values. And both of those, they support different tasks, right? So like if you want to judge where is the largest percentage of, or in which class did, in terms of absolute numbers, survive most people, well, you can see that in first class most people survive, but it also looks like third class, second most people survive. But in terms of proportionality, we see that first class, of course, the majority, like about more than 60% survived, where it's slightly less than 50% in second, and probably less than, well, about 30% in third class. So here is a comparison of the kind of the design choices that you have with bar charts plus a pie chart. Like we have this pie chart, we have 5 categorical values here, 5 keys, and we want to like plot them. So one would be the stacked bar chart. Then we could do a layered bar chart where we represent each of those values by category, or we could have a group bar chart. And again, like these are kind of like faceting, small multiple operations, like each of those is good for a certain kind of task, right? You have to make these design decisions based on the questions that you want to try to answer. Similarly, is true for the stacked area chart. Stacked area charts, however, can be a little bit tricky to read. You can also make a 100% stacked area chart like this. So here we only see the proportions but don't see absolute values. So take a look at this chart. What are the trends that you can observe here? So this is market share of 3 different products or companies. What is the blue thing doing? Yep.
The blue is taking a whole bunch. The green doesn't seem to be changing very much at all, and the yellow is losing a lot.
Yeah, so the green, like what would be your interpretation what the green does? Is like staying...
It stays the same level.
Yeah. So if you do this in the line chart, it is kind of more informative to see these relative proportions, right? You see that while the green, like if you, like I would argue that it looks like it's getting smaller, slightly, but a little bit, but in fact it's getting bigger. So these are kind of like one of these perceptual problems that we have. One of the things why this looks like that is because here, like perceptually, we're measuring from this point here to the closest point on the curve, not up here. So we're not comparing, we're not comparing the height here, but we're kind of comparing the distance here. At least that's my theory on why this looks like that. In this one, can you, this is how many guns are sold. There's different categories: revolvers, shotguns, pistols, and rifles. These are 2 different approaches: stacked bar charts versus stacked area charts. And so, can anybody spot any interesting trends? That's hard to read, maybe. Well, you can kind of see that there's a big uptick around 93, and then there's another uptick around 9 and 10. And that seems to be like pistols. If you look closely here, pistols seem to be dominating, rifles seem to be going down. Yeah. And you kind of can get the same idea here in this stacked area chart. If you represent this as a line chart, the individual trends become much clearer, but the overall impression of the volume of gun sales is really hard to discern. So, well, you still get the peaks because the peaks seem to be driven by sales of pistols. So this looks like some public safety scare probably, but generally speaking, it's harder to judge the overall volume in the line chart. Okay, another technique here is a very explicit representation of a table. So here we have an interactive table-based representation where each cell in the row is actually represented with a graphical mark. And this is like one really famous technique from the very early days. And I have a nice video for that.
With 323 rows of players and 23 columns of data, we can put the data into a spreadsheet. But even using a 21-inch
So these are baseball statistics.
workstation display, the data requires 9 full-screen vertical scrolls and 2 horizontal scrolls, making it hard to work with. It's hard to find players or see interesting patterns. In short, it's hard to make sense of the information. We've devised a new way of visualizing and interacting with large tables called the table lens, which exploits graphical representations to compress the information onto the display. In this column, at bats, we integrate a familiar bar chart representation directly into the textual view of a table. Some of the rows, those in focus, show underlying textual values along with the graphical bars. Other rows, those in the context, show only graphical representations, thus requiring less space. By displaying the entire table graphically, with only some of it in focus, this 324 row by 24 column table can be shown using a portion of the screen. The table lens displays 30 to 100 times as much information as a spreadsheet in the same space. With a small set of manipulation operations, the table lens allows fluid navigation and exploration of the data. The focus area can be manipulated using control points and/or keyboard commands. The number of cells in the focal area can be increased or decreased. The focal area can be moved to different rows or columns. Since the essential geometry of the table is preserved, multiple focal areas can be created. To facilitate browsing of context cell values, a mouse feedback area at the bottom of the window shows column, row, and value information. The graphical representations make it easy to spot trends and patterns and to isolate outliers or unusual cases. For example, sorting a column can reveal relationships to other columns. Here, sorting career at-bats reveals correlations in several nearby columns. Notice that career hits is strongly correlated or proportional to at-bats. In other words, most players have similar batting averages. Some players stick out from the curve, 2 well-known batting stars, Wade Boggs and Don Mattingly. To confirm these observations, we divide career hits by career at-bats, creating a new column, career average. The batting average curve is reasonably flat, as the correlation of the curves suggested, though increasingly noisy with decreasing career at-bats. Furthermore, the length of the bar shows that Boggs and Mattingly have the highest 2 career averages. If we focus on the salary column, we see that Boggs and Mattingly are paid relatively well for their top-flight batting performances. Also note that salary is somewhat correlated with career at-bats. Team and position of a player categorize players into different groups. Category values are displayed using blips. In focus columns, the blip is colored and positioned in the cell according to underlying value. In context columns, since space may be tight, only color is used to indicate the value. Sorting on position separates the players by category. In other words, all light-colored and positioned blips are brought together. So this red line is all the third basemen. Coding effects can be readily spotted. These isolated blips indicate players that play multiple positions and thus have unusual position codes. Sorting by team, other interesting patterns emerge. First, we can see that each team carries a complete stable of player positions and that the sporadic blips are scattered. Second, notice that most of the teams have the same number of players, though 2 lines are about twice as long as others. This is another coding effect. These lines are Chicago and New York, both of which actually have 2 teams. Nearby, 2 other category columns, Division and League, have become more.
Okay, so I personally, this is probably one of my favorite early visualization papers. I'm a little bit surprised that we don't see these kinds of things in Excel, right? There is no direct embedded rendering. There's these sorting features, this deriving the data feature, but this is like a technique from 1994 and would still be considered pretty fancy if you implement it today in a spreadsheet application. Another one that does this explicit table representation, but more for communication, is Birdifier, and I especially like Birdifier for the quality of its authoring interface. So this is like a tool that you can play with yourself. You can actually, like, if you ever have to create any figures, like tabular figures, you can do that up there. Here I'm going to show you another video.
Columns. When she moves her mouse on top of any tool icon, a tooltip appears at the top of the page to recall its function. Tools are organized in groups. Clara first expands the MISC group and clicks on the H icon adjacent to the first row to mark it as a header row. She does the same for the left column. Then she expands the Shapes group in order to turn numeric values into shapes. She clicks on the circle icon next to the first row of the table in order to turn its values into black circles and squares. She is satisfied, so she presses the same icon on the next row and drags down until the last row. This instantly turns all table cells into circles and squares. Now Clara wants a more compact table. Each row can be resized independently using the slider placed next to it. Moving the slider to the right increases row height, while moving it to the left decreases it. She sets all rows to their minimum size by pressing on the topmost slider, drags down until the last row, then drags left to modify all selected sliders. She does the same for columns. She also zooms in using the provided functionality of the browser. Now she wants to tidy up the table. She drags over all black arrow icons, which immediately rearranges columns by visual similarity, which moves similar countries next to each other. She does the same for rows. Now indicators that are similar are close to each other. To better see similarities, she removes the grid by setting all white separators and black separators to their minimum value. Clara continues to format the table to exhibit more patterns and convey a clearer message. This includes inverting the values of a row, importance of a good pay, to better show its correlation with another one, the household income. She also emphasizes two rows of a specific type by changing their visual encoding, increasing their height and dragging them aside. She encodes women's suffrage year using lines and household income using a bar chart. She can choose to reorder only a subset of the rows or to reorder all rows. Now she can already see country groups with Czech Republic in between that she moves away. Finally, Clara adds separators and annotations to emphasize groups.
So I really like this very interactive way of formatting, this combination of very nice usability, and also some algorithmic support. For example, this reordering, this dynamic reordering based on visual similarity. And then bless you. And then I've shown you this before. This is a piece of my own work. This is about visualizing tabular rankings. So if you have numerical data or categorical data and want to generate a ranking by combining multiple dimensions. And so here, this is a university ranking data set, and we're ranking things like academic reputation, faculty-student ratio, the reputation in arts and humanities, international student ratio, and so on. I've shown this before, so I'm not going to go into too much detail. If you're interested, there's a link to the video here, or more information at this website. Oh, I wasn't planning on doing that. Okay. So next I would like to talk a little bit about pixel-based displays. And in pixel-based displays, and this is kind of like a little bit related to what we saw in Birdifier, but there we could basically choose color or cell size, but here we are mainly working with color. So here each cell is a pixel value, and the encoding is the color order value. And as we've seen earlier, as I mentioned in the beginning, here the ordering is critical for the interpretation. So if no ordering is inherent, you have to use some kind of algorithm like a clustering algorithm. And this is a pretty scalable technique. It works for like 1 pixel per item, so you can actually visualize as many data items as you have pixels on your screen, and if you use global ordering, you can probably even go beyond that. So this is really good for homogeneous data, if we have every dimension has the same meaning. So here is an example of an unordered matrix where we basically cannot see a lot of the patterns. And then here on the right we have an ordered matrix where we can see, okay, there is one big red cluster, here's one big red cluster, here's a blue cluster, and here's a blue cluster, which is not perceivable here. So, like, as in any matrix display, the order here is critical. And just as a comparison, here we have a matrix display, a heat map juxtaposed with a parallel coordinates plot, and we'll talk more about parallel coordinates plots later. And so you can see that also, like, there's two groups, two distinct groups, and you can see those easily here, like a high cluster, low cluster versus low cluster, high cluster. And this is also visible in the parallel coordinates plots, but just to see the relationship between those two. Who can spot the pattern here? What is the pattern? Just shout out if you see it.
City skyline.
Skyline? So Manhattan. Just to give you like a little bit context here, this is a pattern that is hard to spot. This is just like one more time saying that 3D can be problematic. If you look at something like this in a heat map, it is pretty clearly visible what is going on, right? So we have this question mark, which is very obscured in the 3D plot. And we'll actually have a counterexample today where 3D is actually more valuable than just a color representation. So it always depends a little bit on what your data is. You can also try to do these heat maps for very different data types. So here, this is a pharma figure from a prominent paper, a genetics paper. And so each of these rows here uses the same color scale, or almost the same color scale, but they show different data. So here this shows mutation data, this shows gene expression data, copy number, mutation data, gene expression, copy number, mutation, and so on. So I would argue that this is possible, but not very intuitive. So I would probably argue for using at least a better separation, or different color scales, or just take a completely different approach. And again, a reminder of the problems of color mapping. So up here in this heat map, we can see that there is, like in a red-green heat map, which is still very common in biology, we can see that there is this like high red value, and then right next to it there are a lot of low green values. But if somebody is red-green blind, this effect, this very strong effect, is completely lost, because we have this, the value is high of the colors are very bright, and the separation by hue here doesn't work for somebody who has red-green blindness. If you instead did something like this, so you have this exact same thing, like you have high values juxtaposed with low values. If you have a red-blue color map and have normal vision, it looks like this. For somebody who is red-green blind, it still is readable easily. So just a reminder to use good color mapping. And also, one of the problems with heat maps is that color is relative. Also, we talked about this in the perception class, but those two colors here are actually the same, but they don't look it, right? This one here looks brighter than this one, just because of its surroundings, just because here are darker colors in its surroundings, here are lighter color in its surroundings, so this one, we perceive it as darker than the one up here. And so, just to give you another example, like a textbook example, here we have the same color and this one looks different, here we have different colors and they look the same. So, if you use heat maps to visualize data, always be wary of these effects. However, they're still very useful tools because of their scalability. So this is a heat map that shows about 1,500 dimensions and 500 rows. So this is like a massive data set, and you can see big patterns here. So this is even that you probably, the screen doesn't show you every pixel here, but you still can get the major patterns. You can see that there is like a low band, you can see that there is a couple of distinct clusters here, and so on. If you try to do this with parallel coordinates, you're basically only getting like a very messy picture. You can see some of these boundaries between the clusters, but they're not very easy to spot. So the scalability of heat maps is unsurpassed. You could also do multiple line charts. So like this uses a technique which are called horizon bands. So instead of like this is the original data here and at the top. This is the data scaled down, and here the data is wrapped around once or multiple times. So you can see like the bar here are like they're so high that this is clipped off and attached again from the bottom, and in this case even twice. And so there are studies on that. Like here you can see another 3 times wrapped around. There are studies on that, and people are actually pretty good at perceiving these kind of horizon graphs. Here is another combination of various charts. So this here is similar to the heterogeneous matrix, but a little bit different in terms of that we use different visual encodings for different data types, right? So here we show like copy number data, mutation data, so mixed categorical and numerical data. But they are like each of these rows that has the same semantics, uses the same visual encoding and the same color scale, and each of the rows here that have a different semantic, they use a different encoding. So here, for example, gender and race, they use different color scales just to make it clear that they are actually also different. And what this also does is a dynamic aggregation. So here, instead of showing every single value in this column, we only show a summary. So here we show the summary either as histograms or potentially also as box plots, whatever the user prefers. And here we show the summary as box plots. So this is like you can dynamically switch between those various representations. And so this is like, you can get a good idea of what the distribution of the underlying data is, and if you need to know more, then you can expand those, switch them to individual representations, and then explore the details about them. Okay, so now I'd like to do a design critique about a 3D information visualization. So the links are here, and I'll hand out the sheet. And I recommend that you go to the New York Times website and play with it, because it only works well with interaction. Talk to your neighbors, try to answer the questions that you have here, and then we'll discuss this in 5 minutes.
If anyone's still trying to access it, I think in this URL it's a capital I, not a lowercase I.
Yeah, you search. Yeah, I think dark is high. It's essentially it's even. So it's reduced to 2.5 instead of 3D. So it's not flipped out. Why is it necessary? From your bonds or something. But also, oh yeah, you see this is not on your scale. Which is fine actually, because I think it's over. No, it's not. This is not done. Like that's not ratio. It would be probably like set rates for 1 month, 3 months. So I think that's okay actually. So it's a going basis.
Okay, so let's talk about this. What is the data that we see here?
Interest rates.
Interest rates, yes. Over?
As a function of time and as a function of the duration of the loan, I guess.
Okay, so we have 3 dimensions, right? We have time, we have the value, like we have the values of each, or 2 dimensions. We have time, and then we have the length of these of the loans, and then we have for each of these cells we have the values here. Okay, so what are the marks and channels that are used here to encode the data?
Color and position.
Correct. Color and position. So color and position is used in which way?
Dark is high rates, white is low.
Yes. So we have a redundant encoding. So this, like, high values are encoded both by high, like by height and by the color. What do you think about the 3D effects here?
I think it provides a lot of context, especially with how it moves from point to point and telling the story. It really helps you understand what the data are and what they're showing.
Yeah, so movement and interaction is important because like, if I look at it like this, it's probably not very informative, right? But I can actually move this around and then get like a view from every side to it. Any other opinions? Like, I told you all the time 3D is bad, right? Any comments on the use of 3 dimensions here?
No, in my opinion, I think it almost works, but the problem is that you can't filter the data by the year or anything. So it's like, what's the point of having a 3D? It's just deterring you from what's actually happening because you can't get any precise data out of it, if that makes sense.
Okay, this is a good question. Like, do you think that the goal of this visualization is to be able to read the exact 5-year value in the year 94?
Well, no. For example, if you look at it straight on, right, you're only really able to see, even assume what the 3-month span is. Do you understand what the 1 month look at it?
The very short-term loans?
Yeah. So if you wanted to look straight on and see what a 30-year loan is, it's kind of more difficult, I guess. Well, you could lower it around and stuff.
But that's where the color comes, it can help you.
Exactly. So, yeah, I get the point, but the redundant encoding is actually like kind of helpful. And so if you compare this view that you have here with this 2D view that contains all of the same information, which one do you like better?
I like being able to flip back and forth for context and detail.
Well, if you have to choose.
What's your goal?
So, or there's another 2D view here. Like this shows you the same data as the 3D charts, right? But do you feel like you can, like this is a heat map. Do you feel like you can read the data as well?
You lost the dual encoding, right?
Yeah, you lost the dual encoding. And so, like I would even argue that the 3D here provides an added benefit. Like, does somebody disagree? So what makes this data like special? Why is this suddenly like a good 3D chart? Any opinions?
I think because it's interactive, so you can play around it and build a actual shape in your mind and have a sense, and also using the color shade helps you to better understand the difference of the height.
Yes.
And also using the grid on the surface, and so helps you to follow the.
Yeah, so there are a couple of good design choices here. The interaction in 3D, if you have to use 3D, you have to provide a way of navigating. Like that's critical because then you can avoid occlusion and so on. And then we have the grid lines that also help us, and we have the redundant color encoding. But there's something else that I would like to get at.
I don't know if this is what you're thinking, but there are some fast changes, but none of them are huge, and so you may not be able to see everything. There is some occlusion, but it's not terribly difficult to interpolate.
Yeah.
Get a decent idea.
Exactly, you're hitting exactly the right point. We have like a nice hull here, right? A continuous. So there is nothing that is occluded which we cannot somehow mentally interpolate because we have this flow. So we even without knowing what is exactly behind this big peak here, we kind of see that it's likely not to like go up in the middle here. So this data is kind of like uniquely, this continuous nation of the data makes this again interesting, like a good 3D, a good representation for this data set. So what do you think about the storytelling aspect here?
I mean, I liked how they jumped to kind of more two-dimensional perspectives to show more detail within the context.
Yeah, so like the stepper here provides two different aspects, right? We have like context information, how many steps there are, where I'm standing at. I can straight jump to any of those states, and I have this back and next slide, and then all like what is the operation that these steppers do?
Change your camera point.
Exactly. It's mainly viewpoint changes. It's a rotation to a specific position. There is some additional stuff here. They dynamically add annotations, of course, to highlight the point they want to make. And then at the later point, they also switch data sets. So this transition here for Germany and Japan. And I would again argue that this picture here is less, like it contains exactly the same information, but somehow it feels less tangible than looking at this like this. So, any like comments? Do you like this or you dislike this?
There's some missing shading cues in this that makes it really kind of hard to follow as you transition. Because I don't know if it's, you can really call it the color scale because it's mostly shadows that are missing, so the 3D form gets lost, I feel like a lot.
So what would be the trade-off if I used like proper 3D lighting here?
You wouldn't be able to see the proper colors and
Yeah.
really compare it against it.
Exactly, so I would get better perspective clues, but I would kind of like have less of a color perception.
It might even be like just darker lines that they have, like the topology lines almost that are going on that would help with that. I think you could do that without changing the color scale, just changing the, instead of white, make them all black or
Yeah, 'cause
darker.
the white blends into the lowest point of the color scale. So
Yeah.
you do lose a little perspective in there.
Okay, any other opinions?
I just want to say, if we use a darker color though, then it heights it up in the higher levels, so either way it's going to be difficult.
Yeah.
Maybe dynamic grid lines,
Yeah.
darken them up as you get into the lighter areas of the.
Yes, that could be like a fancy implementation.
So I'm curious, how would you generalize kind of the principles that make this a good use of 3 dimensions so that we can kind of know when it's appropriate and when it's not?
Well, I would say if you have like a continuous data set like this, here we have a two-dimensional continuous data set where we have a shape that is, so in the example that I had earlier with the question mark and bar charts, there was a lot of occlusion going on, and it wasn't a continuous data set. But here we have this nice and smooth continuous data set, which is the reason why I think that this chart works.
There's something else inherent, I think, in the shape of a year-to-year yield curve, that, like the shape of the curve in each year itself yields like almost an additional data point
Yes.
in terms of how people think about what the yield curve is. So I think that's the other part that makes it useful to see that shape and how it changes over time.
Yeah, exactly. We kind of see two line charts here, right? We see the line chart over time, and then we see the line chart for the length of the loans. There's another subtle detail here that is done well. If you look at the labels, what could you do wrong with the labels? So these labels, yep.
So the interest rate ones they make it look like it's a linear scale, and it's like roughly kind of close to a log 2 scale,
But it's
but
ordinal.
it's really not either of them.
I think that's ordinal data though, so I don't think it
Yeah.
matters.
But when you connect everything continuously, it makes it look like it's not ordinal.
That's a good argument. I haven't thought much about it, but this is a good argument. Yes, it's ordinal, but it's not like it looks like linear. So yes, but that's not what I was trying to get at. What would happen if you did a naive implementation of those labels if I start moving this around?
I think the labels are based on the point of view, and you always facing the right direction of the label.
Exactly. So the labels are really like billboarded here. They're very well done. They're always horizontal. They're never tilted, so they're always readable. And that's also what makes the 3D chart very effective, I think, or it is a of critical importance that this is actually the case. Okay, any last comments? Good, so let's move on. Okay, next I would like to talk about spatial axis orientation. And so we'll be talking about rectilinear, parallel, and radial layouts. So here are the two major rectilinear and parallel layouts. We will like scatter plot matrices, and parallel coordinates. So here you have like an example of how these two correlate to each other. So we'll talk about them in a little bit more detail. So here we use spatial axis orientation in a scatterplot matrix. And so scatterplot matrix, or also SPLOM, is a matrix of size d times d, where d is the number of dimensions. Each row and column is one dimension. And each cell plots a scatter plot of 2 dimensions. So here we have this classical iris data set of flowers with sepal length, sepal width, petal length, petal width. And you can see that we see every relationship in this data. So we have 4 dimensions, so we have a 4 by 4 matrix. What is the property of this matrix? So like, if you look at the symmetry, we see that it's actually a symmetrical matrix. So like, the information here is redundant to the information below the matrix. And of course, this is always a perfect linear relationship, because the relationship of the data set to itself is split linear. So here in this data set, we can look at each cluster and can see that this one, the color here is used to differentiate different plant species. And we can see that in some dimension combinations, there is this clear separation of the red and the green-blue ones. So like in these combinations here. It is not so, well, it's still pretty obvious here, but then the green-blue one is more mixed up in these other dimensions. So here I can really see every single dimension and every single combination of a dimension. So what could be one of the drawbacks of this technique? We're using a lot of space already for a 4 by 4 matrix, right? So if I have more than, let's say, 5 or 10 dimensions, this can get pretty big.
Right, I'm not clear, where's the symmetry you were saying?
The symmetry, this chart here corresponds to this chart here. It's just flipped over.
Okay. Okay.
So along the diagonal, you wouldn't need those at all. And sometimes people actually use these the upper half of the scatterplot matrix to visualize something different. And then it's also very common to show a histogram in here of the distribution of the actual value instead of the explicit scatter plot. So this is kind of limited in terms of scalability. So you can probably show on a regular computer screen about 20 dimensions and about 500 to 1,000 records. Brushing is critically important because, if I didn't have this color coding, I wouldn't know which of these elements here correspond to the elements here. So there is no explicit relationship of these items between the different plots. And it's very often combined with the focus scatter plot, so that I can pick one of those scatter plots from a larger matrix and then look at this one in detail. And what you can do to algorithmically improve these scatter plot matrices is something like clustering or aggregating records. So this color coding, for example, is something that you could derive from a clustering. Choosing the dimensions, if you have a very high dimensional data set, you can do something like a dimensionality ranking and pick dimensions dynamically, and then also choosing the order in which you present them. I've shown you this example before. This is an aggregated scatter plot matrix. I'm not going to go to this website again. But here we have these characteristic histograms in the diagonal, and here instead of having the points here, we have these density maps with the brushing. This is a very nice technique that uses exactly what I mentioned earlier. Like a scatter plot matrix is an overview where I can see these trends, but then I can pick one of these views in detail And this is actually a paper that that investigates navigation methods in these scatter plot matrices, and it does so in a very nice way.
This application is a prototype implementation of our scatterplot matrix navigation technique. Scatterdice consists of 4 main components: a scatterplot matrix, a query layer control box, and a navigation bar. The main scatterplot visualization shows the current position in the scatterplot matrix, in other words, 2 of the dimensions in the dataset. A set of simple navigation techniques allow for controlling the position in the scatterplot matrix. The keyboard or the navigation bar can be used for stepping one position in the matrix at a time. Movement is performed as an animated 3D transition from one scatterplot to another, where one dimension remains constant. The user can also scratch the current position in the matrix to see the animated transition from one dimension to the next. To move directly from one part of the scatterplot matrix to another, it is also possible to perform a hyperjump. If the user wants to see the intervening positions, the path planning interaction transitions automatically from one position to another. Finally, path drawing allows the user to draw the path to traverse on the surface of the scatterplot matrix. Scatterdice allows the user to build queries using the query layer box and a lasso tool, and then see how the queries distribute in other plots. The user can move an eccentric label lens on the plot to see the nominal names of the data points. This also works with query selections. Finally, the rows and columns of the matrix can be reordered, either manually using drag and drop, or automatically using the pairwise correlation of the dimensions. We will follow a user who is employing scatterizing.
Okay. So I would argue that these transitions are like a little bit radical, and it's hard to keep track of what is going on, but this general idea of having like the scatterplot matrix here as an overview, and then being able to navigate through that and seeing this detail is a pretty good one. Okay, so next I would like to talk about spatial axis orientation, specifically parallel coordinates and later star plots. So in parallel coordinates, we have seen them a couple of times, but formally now, axes represent the attributes or the dimensions, and the lines connecting the axes represent the items. So instead of having, like in a scatterplot, x and y orthogonal to each other, they're parallel.
Sorry, can I just ask one more from the previous one?
Sure.
On the, just the general, with the ordered scatterplot, symmetric plot, isn't that also an ideal place, especially when you have data that have a lot of correlations like this, to do like a PCA to better visualize the redundancy of the data set, especially when you have a lot of channels?
Yes, definitely. So like scatter plots, you can like just visualize PCA instead of showing the raw data. Yeah. So like there's a good combination to be made here. And if I have the time, I have a couple of slides of PCA left over from the last lecture. And if not today, I'll fit it in some other time. Okay, so in parallel coordinates, like here, how would those 2 points look? X and Y as dimensions, A and B here as the items. We have A is high in X and low in Y, B is high in Y and low in X. And so these would be added to these axes here and then connected by lines. So I see that A is high in X, low in Y, B is low in X, high in Y. And I get this crossing here that visualizes this trend. So these are like the equivalent plots of these 2 techniques. And what makes parallel coordinates nice here is that I can continue on with more dimensions on the right. So here I give a larger example. Each axis represents 1 dimension and the lines connecting the axis represents the vectors. And this is a great technique because it is suitable for all tabular data types. So like unlike a heat map, for example, we can plot categorical data here, we can plot data of different types here. You can basically fit anything on these axes. However, there's a couple of drawbacks. So one of the problems with this is the scalability, and so we've seen this earlier, the scalability to many dimensions is pretty limited. Then also the scalability to many items is pretty limited. This is actually like something that I did in my first 3 months of PhD. I tried to render a parallel coordinates plot, and then I created this chart, and I was very frustrated because it was useless. So a simple fix for that is to use transparency. And transparency automatically kind of gives us an aggregate here, and this is randomly distributed data, so we can see this random effects here. However, like picking the right alpha values depends a lot on the patterns in the data, and it depends a lot on the number of elements that you have. So like picking the right transparency value can be difficult. What you could do in addition to that is something like sampling. So you could instead, if you have a lot of records, if you have 10,000 records, it actually, let's just observe the major trends in the data set. You could just plot a random sample of, let's say, 500 lines. And so you would still be able to see all of the trends. Of course, you could miss one or two outliers. You could also use clustering and bundling, and I'll have a couple more slides on this. Another limitation here is that we can basically only see relationships between two neighboring axes. So we can, for example, here displacement versus the year built is really hard, or it's impossible to see, because I would have to manually trace these lines. Where do they go? So one potential solution, chemically, interactively, explore the relationships between these dimensions. So now I can see like the miles per gallon versus acceleration here, or I can easily see displacement versus horsepower, that this is like a roughly linear trend. Another problem is that in detail there is ambiguity, right? So in this case, like if I have two incoming lines to this axis, line A and line B, I don't know whether this is now line A or line B. The same here for this chart where I have this incoming polyline, but it's not clear whether this line here continues up here or down here, whether this line goes up here or down here. So we have these ambiguities here. There is, of course, the obvious way to resolve this ambiguity by brushing, or you could also use curves. And if you use curves, this goes away. However, curves, like, this is not really a big problem if what you care for is mainly trends. This is more of a problem if you want to like see details about each individual item. So, like parallel coordinates, they show a primary relationship between adjacent axes. They have limited scalability to about 50 dimensions and 1 to 5,000 records. You can work with transparency lines. If you have more than that, you have to like be a little bit smarter about, for example, algorithmically choosing the dimensions, algorithmically choosing order, using clustering and aggregation of records. And for parallel coordinates, as for many high-dimensional and more complex visualization techniques, interaction is crucial. You access reordering, brushing, and filtering. And so, like a word of advice, if you were into visualization research, there is 1 billion papers on parallel coordinates and little extensions and 3D versions, and combining them with scatter plots and so on. It's like a topic that has been beaten to death, so I wouldn't recommend that you invest a lot of time trying to reinvent the wheel here. But still, they're useful visualization techniques. This here is an idea to use hierarchical clustering to enhance these parallel coordinates plots so that we can scale up to larger data sets. So like this is an example where we can still see the trends in here, but then here we basically only see the how of these plots anymore. So how can we get rid of this overplotting and occlusion? And so this hierarchical parallel coordinates idea is that we cluster the data using a hierarchical clustering algorithm, and then dynamically like slice the clusters, and then represent the cluster plus like a deviation from the cluster centroid as these shaded bands. So I get this bigger trends here instead of like I see the cluster centroids plus their distribution instead of each individual items. And so here is an example of like this is the same data in a hierarchical cluster data set at different cutting levels, right? So here everything is treated as one cluster. Here we have 4 different clusters. Here we had more, 5 or 6 clusters, and then a lot of clusters. So this example isn't very great, I would say here, but generally this is a neat idea that could work for many cases. A very close relative of parallel coordinates is the star plot. They, like, instead of aligning these axes in parallel, they are simply radiate from a common origin. And you probably have seen those a lot. There is, I like this example that characterizes whiskeys. According to their, like, are they malty, fruity, floral, what's the body sweetness, and so on. So you can kind of like treat this as a glyph and see how similar two whiskeys are based on looking at these shapes and these glyphs. However, like, my personal judgment on this one is it is not like what's done here is that these whiskeys are all shown as one star plot each. So as glyphs, they're kind of useful. But if you do it like we have it here with many of those in the same star plot, it gets overplotted pretty quickly, and also like down here, like the closer you come to the origin, the less space you have to visually represent them. So typically, star plots are used, if at all, as these glyphs, and not so much as like showing multiple variables in the same plot. So, like, a couple of methods for data reduction, and we talked about this in the filtering and query lecture, but just to repeat it. So the sampling here, this is from a paper where between those two dimensions here, it's not sampled, between those two it's not sampled, and here we have a random sampling. So here we can clearly see trends, here it's massively overplotted. This is very efficient for a large data set. One thing, if you use this, you should take care, if you implement this, that you, like, for example, if you have dynamic queries or brushes and so on, that you apply the sampling only for display purposes, but if you run a query, that you run the query still on the whole data set. And there's also some outlier preserving approaches, so that computationally look for outliers and preserve these outliers in these plots in the literature.
Can you go about the sampling a little more, I guess, robustly by doing like a decimation or something like that, as opposed to just random sampling of the data set?
Yes, you can. But there's like this paper specifically actually compares a couple of fancy sampling methods to random sampling methods, and they didn't find any significant differences in what people learned about the data sets. So you can always make it fancier in terms of the algorithmic approaches. It might be useful for particular data sets, but in many cases, random sampling is pretty satisfying. And then we talked about filtering generally. So, like, parallel coordinates, they have a very intuitive way that I can dynamically filter on the axis. So it's like in heat maps, for example, saying I want to just it's not clear where I would touch the data to say I only want the light blue to dark red values. In a parallel coordinate, I have an axis where I can simply say this is the region that I want, or this is the region that I want on this dimension. So I can very dynamically define those queries. And so there's also research on comparing these queries to, for example, SQL queries for database experts, and even the database experts found this to be very intuitive. So with all these spatial axis orientation things, I can actually also develop hybrids. And these hybrids, like one interesting paper here is this FLINA paper, Flexible Linked Axis. And the idea here is that you simply define and position these axes dynamically, and then say either scatter between these axes or draw lines between these axes. And so this is a simple idea. You can actually create scatter plots, parallel coordinates plots, radar charts, or this hyperbox, this time wheel, or many-to-many parallel coordinates. So you can create these intricate visualizations here. And they actually also develop a grammar to build those. And here is a web-based implementation of this, where you can actually draw your own FLINA. So here, this is again the cars data set. I can say, let's draw miles per gallon as an axis. Okay, let's do it like this. Position it. And so you can already see that there's these dots that are positioned on the axis. And then I can add the displacement as an axis. And then can show lines connecting those axes. And then I could add the horsepower as an axis. And then I could define to scatter between them. And so I can build up these visualizations here in a very dynamic way. There's also color brushing and some statistical analysis and machine learning built in this tool. So this is a very flexible way of creating these axis-based visualizations. And of course I can also like make designs that are a little bit crazy, like this for example. I can like add more axes, can make all of these radial layouts. Another way of thinking about this, if we have multiple views, we can also connect these charts. So this is an example from Michael McGuffin's lab. And so here this combines line plots with scatter plots and then connects all of those with these lines. And so I can see these major trends. And then here is basically a parallel coordinates plot in between those two different views. Network uses, hard uses, seems to be somehow anti-correlated. And then we see the same for CPU temperature and program usage. Seems to be, interestingly, low program usage is high CPU temperature. That's kind of counterintuitive. But there is examples where high program use, well, I'm not sure about the data here, but essentially this idea of showing these explicit connections for each of these data points and then using a mix of parallel coordinates and scatter plots is also interesting. And I've shown you this one where this is a piece of my own work which combines even these pixel-based representations, the heat maps, with individual axes and then with scatter plots and also then with categorical visualizations. So that you can build a complex visualization on a desktop similar to this flexible linked axis concept, but even more general. Okay, and then the last thing I think that I wanted to talk about today is spatial axis orientation for categorical data, specifically parallel sets. And parallel sets, they kind of build on this idea of parallel coordinates to better handle categorical data. So if I were to draw a parallel sets plot with categorical data, I would get something like, I have an A, B, C, and then I have two categories here, and I would get these like very densely connected points. It would be hard to spot anything because there's no variation, right? Because I have a discrete position. Takes this idea of parallel coordinates, but instead of representing this as discrete positions on the axis, it shows them as bars, and then represents this as instead of lines, it represents ribbons between them. So the boxes here are scaled by frequency, and the color coded are the values for the currently active dimensions. So again, a Titanic example. Here we have first class, second class, third class crew. We can see that third class is the biggest chunk. Crew is also a pretty big chunk, and then here we have sex, female versus male. We can see overall in the Titanic there were more men on board than women, and the crew was because we see this like very wide ribbon connecting straight to the male block. We can see that the crew was predominantly male with a couple of few outliers here that cross over. We can see in the first class there was like a roughly even split between females and males, whereas in third class there was like there were a lot fewer females than males. And so this can also be augmented with histograms in between, but generally these parallel sets are like a pretty neat idea for visualizing categorical data. One of the interaction techniques that is important is reordering, because the chart depends a lot on the order, how complex it gets. So I can switch over crew and third class here to get a more, to get a little bit of a cleaner chart. And there are ways of interacting with this. For example, I could filter, I could remove all of the third and crew here, and then I see only first and second. Or I could highlight dynamically but all of this is probably better explained in a live example. So this is a D3 parallel sets implementation. I can hover over any of those ribbons, and it will highlight how this ribbon splits up across the where this ribbon continues in these various domains. And then I can also switch this over. Interesting. Something seems to be broken here. Okay, but I should also be able to switch this horizontally. No. Okay, this seems to be somewhat broken, but I think you get the basic idea of how the brushing works, how the highlights work, and how this shows the relationship between these dimensions. Okay, so, well, I'll quickly do this so that we can fill this out. You can also do these dense pixel displays, and this is more of like a historical node. Here you can represent each data item or each attribute in an item as a single pixel, and then try to fit each of these on the screen. It's kind of related to a heat map, but it has it's not for these homogeneous matrices. I can kind of create this this dynamic layout, and so here it's, for example, one of these ideas was to order it in a spiral, what you can then do is these nested things. For example, you have one glyph with 6 dimensions, and then you order them according to some ordering pattern, and then you visualize them like this. This was a big deal in the 90s, and there's a lot of papers, and these people made great careers, but in the end, I'm not quite sure how efficient they are at really showing data that is understandable. So this is more of a historical node. And that concludes today's lecture, and I'll see you guys on Thursday when we talk about graphs.